Yes, welcome back to today's explanation of the Boas cuboid models. Today we are looking at the Boas cuboid model. We had looked at the cylindrical model and we saw how it works, and we did some applications, and we also saw how they are really applied in the real world problem. So today we are going to see about the cuboid models, and we are going to begin with the derivation, of course, then the equations and the applications of the model that is brand new, and it's called Boas cuboid model. Now, introduction. Boas model, it relates the surface area, the volume, and the dimensions. It's a model that connects the surface area and the volume and the dimension of the 3D object system, like in this case you're dealing with an cuboid. Applicable in optimization scenarios like tank design and many others. So let's go ahead and see about these cuboid. So the geometric part of this cuboid model, we have the dimensions as A, B, C as the length, width, and the height respectively. Then the surface area of the closed, that is the formula, and then the surface area of an open top, and that is the formula, and the volume V is equals to A times B times C, also that is the formula. So today I'm going to combine the two systems, both open and closed. We are going to discuss them together and see how they are applied and how they are going to work for us as the engineers. So that's the geometric part. So Boas optimization model, let's begin with the closed cuboid, the closed system. We have there the surface area as 2 into AB plus AC plus BC, and the volume V is equals to A times B times C, as we know. And then C there is the expression of the height from the volume. Given V is equals to ABC, then C is equals to V over AB. And then we are going to have the final function, which is the model, f of FB is equals to 2A squared B squared minus AAB plus 2VA plus 2VB is equals to 0. Now let's go and see how this model came about. That's what we are going to see, because I know you're asking yourself, why did I decide to make it to be 2A squared or B squared minus AB and all that. So this is how the journey began. We have the surface area as given, 2 into AB plus AC plus BC. Then making C the subject from this expression of a surface area, we are going to have C is equals to A minus 2AB over 2 into A plus B, and that is going to be our equation number 1. Then from the expression of the volume, as we had written up there, C is equals to V over AB, and that's going to be our equation number 2. Then as you can see, and it is obvious that the expression of their height are equal. So equation 1 is equals to equation 2. So that's what I've equated, as you can see. That implies that A minus 2AB over 2 into A plus B is equals to V over AB. That one is going to be our equation 3 for that expression. Then simplifying equation 3 into the form AX squared plus BX plus C, which is the depressed function, as we said, we have a function as the model, which is going to be simplified as 2A squared B squared minus AAB plus 2VA plus 2VB is equals to 0. This is the model, and this is how that model was derived. So that is the derivation part of that model of the closed system. And A is there stands for the surface area, and the V stands for the volume, as we said that it connects the area, the volume, and the dimensions of the cuboid system. And now let's go and do the most economical part of this optimization model. Now here we want to optimize this model. We have to optimize this model so that we can know the optimal dimensions of the cuboid system of any most economical system. So there we have, we are going to compute the derivative of the function as it is written there. Then you're going to set it to 0, because this is how we get the maximum or the minimum of the any function. If we differentiate it, then we are going to have it as either maximum or the minimum. Here is just looking at the extreme points. As you can draw a curve, then you're considering the extreme points, the highest and the lowest, so the maximum and the minimum. That is going to be considered as the most economical model. So in our function, we are going to have a d partial derivative of f with respect to b, then you're going to multiply with the partial derivative with respect to a. Now let's go ahead first and find the partial derivative of the function with respect to b, and then you're going to differentiate the partial derivative of f with respect to b. You're going to differentiate it again with respect to a. That's what we mean by d into f with respect to b is equals to 0. So as you can see, we have there the derivative with respect to b is 4a squared b minus aa plus 2v. Then you go ahead and differentiate this with respect to a, and that's what you are going to have. You are going to have 8ab minus a is equals to 0. Then of course, setting a the other side, you are going to have surface area, which is a is equals to 8ab. This is the surface area of an optimal or the most economical system of a cuboid that you are going to be given, of course, of the closed system. So the total surface area A is 8ab for most economical system for optimization purposes. And then we are going to have there A is equals to B. For most economical system of our cuboid models, A is equals to B. That means length is always equals to the width. Length is equals to the width. We are going to see that how it can be proved. For now, let's go ahead and look at the open system now. For the open system, we are going to apply the same procedure as we have done to the closed system. We have the area as expressed there and the volume, and then making C from the volume as a subject. That's what we have. And then the final expression as the model is a squared b squared minus aab plus 2va plus 2vb is equals to 0. Now let's go ahead and see how that one came about. Following the same procedure, we are going to express C from the expression of A as that, and then V as that, and we are going to equate these two expressions of the height, which is C, and then simplifying it, we are going to have the model as a squared b squared minus aab plus 2va plus 2vb is equals to 0. That is the model, and that's how this function came about, and that's how it has been derived. It's just a simple geometry, and then things are being made up. So the most economical part of this, we are also going to do the same thing as we did to the closed system. We are going to have that kind of partial derivation, a derivative. Then we are going to have surface area. In this case is 4ab. In the other case it was 8ab, but in this case it's now 4ab, and of course A is still equal to B because it's most economical system, and A is the total surface area. Now that's what we have, and the economical models are now closed cuboid. Of course A is equals to B, and A surface area is equals to 8 times A times B, which is 8 times length times width. That will give us the surface area of any most economical cuboid system, which is closed. And then for the open top cuboid, we are going to have A is equals to B as obvious, but surface area is going to be 4 times length times width, which is 4 times A times B. And that is that. And the applications of the economical part of the optimization is one of them is packaging design, tank, dams and reservoir optimization, and then we are going to have architectural and manufacturing. And that's how this economical application of this model is going to be done. Now we can go ahead and look at real world application, practical application. And here we have question number 1. Very fast, this is going to show us how Boas model is being used, and it's very important, especially in things to do with optimizing, making more profit. Economical part application for this model. We have county government of Kisumu is planning to construct a most economical dam to control floods as one of the projects of this year. The dam is expected to hold a capacity of 48,000 meters cube of water. The surface area of the land provided for this project is 64 meters squared, which has been declared minimal. They wish to maximize this land and are assigned to be the chief contractor of this project. Using Boas optimization model, Roman 1, show that for any most economical cuboid system, the length is always equal to the width. Then Roman 2, compute how deep the dam should be dug to maximize the minimal area provided. Hence, find the possible measurements of the length and the width of the dam. Then the last one is to verify that the results above are optimal. Look at this kind of a question. They said that the land provided for this kind of a project is very, very minimal, and of course, as you can see, 64 meters squared is very minimal to hold 48,000 meters cube of water. That capacity seems to be much more than water 64 meters squared can hold. So you have been provided with this kind of project, and you as the contractor, they are depending on you, and they are counting on you to do your magic so that the 6400 meters squared of land can be utilized, maximized enough to hold this capacity of water. So you have been provided with this kind of a project so that you help the management of Kisumu county government. Now let's go ahead and see how Boas optimization model really works for such kind of problems and such kind of projects. So starting with the question 1, show that for any most economical cuboid system, the length is always equals to the width. Now the solution. First of all, you have to understand that a dam is an open system. A dam is an open system. That's number one thing that we have to note down. So having noted that, so that one is going to help us to decide on which model are we going to use. So of course, we are going to use the open system cuboid, and the function for that is a squared b squared is equals to aab plus 2av plus 2bv is equals to 0. This is what we are going to use in this case. Now we want to show that the length is equals to the width. This is what we are going to do. We are going to find the partial derivative of the function with respect to a, and then we equate it with the partial derivative of the same function with respect to b. Because you can see this model, it has two variables, a and b. A and v are constant. So the first one, df over dA with respect to a, that is, we are going to have 2ab squared minus ab plus 2v. And then again with respect to b, now the same function, we are going to have 2a squared b minus AA plus 2V, and then equating them, this is what we are going to have. 2AB squared minus AA plus 2V is equals to 2A squared B, minus AB plus 2V. Then we are going to compare these terms, because as you can see they are equal, and so we are going to compare the terms as they appear on the right hand side and as they appear on the left hand side. So beginning with the first term, that's what we have. 2AB squared is equals to 2A squared B. If you simplify that, you are going to remain with the B is equals to A. You compare the second terms, which is very quite simple. That we have negative AA is equals to negative AB on the other side. Then A and A will cancel out, and we are going to remain with A is equals to B, which is the same as B is equals to A. And that's how we are going to show that the length and the width of the most economical system of a cuboid is equal. That means the length is equals to the width, and that's how it's done. Question number 2 says, compute how deep the dam should be dug to maximize the minimal area provided. Hence, find the possible measurements of the length and the width of the dam. This one is now very simple, because with Boas optimization models, things are made easy. Now, look at the question. They said that the area is minimal, but they want to maximize it. Remember, A is equals to B. They are fixed, because once somebody has given you a land, you have purchased a land and he has given you the title deed, we don't have any other option to extend the length or the width. So the only thing you can do is either to maximize the height or maximize the depth, because the length and the width are fixed. They are equal. In this case, because it's the most economical, they are equal. Now, having that, we are going to use the economical surface area of the cuboid system. Using Boas optimization model, we have 4AB as the surface area of the most economical system according to Boas model. So we were given the area as 6400 meters squared. So we are going to equate that as 4AB is equal to 6400 meters squared, and then we are going to have down there A times B is equal to 64, because we are going to divide 64 by 4, and we are going to remain with the A times B is equal to 1600. So then C, which is the height, is expressed as V over AB. We were given the volume of the capacity as 48,000 meters cubed. Now what we are going to do, we are just going to substitute V and the value of AB into the expression of that height, and then we are going to have 48,000 over 1600, and then C is going to be 30 meters deep. So this means that for you to maximize this piece of land, the dam must be dug 30 meters deep in order to hold that capacity of 48 meters cube. So that's how you are going to be that's how you are going to maximize that piece of land. Now let's go ahead and find the possible measurements of this kind of dam, and now the length and the width. Because now we have the height, things are now very simple. You can simply take the value of C, 30 meters, and insert it into the expression of C, and then you are going to do some simple substitution, and boom, you are going to have the length and the width. Now since A and B are equal, it is right to say that A times B is equals to A squared, or A times B is equals to B squared, because they are equal. That means A is equals to B, which is equals to the square root of the 1600 that you are given, that we found or computed up there, and that means we are going to have A is equals to B is equals to 40. Of course, I know the square root of 1600 is either negative 40 or positive 40, but logically a dam cannot be negative 40 meters. It can't be. So we have to work with the positive term, which is 40 meters, and A is equals to 40, B is equals to 40, and the height is constant, is equals to 30 meters. So that is the dimensions of the this dam that can maximize this piece of land that is minimal. Now let's go ahead and do the third question, Roman 3. Verify that the results above are optimal. For you to verify or to be sure that the results are, or your calculations are optimal, we are going to use Boas model to verify that. This function is going to help us a lot, and if this function is satisfied for A is equals to B is equals to 40 and C 30, A surface area 6400 and the volume 48,000, if you insert these values into the model, and you are going to have such a thing as I've computed, and my results were as follows: negative 7,680,000 plus positive 7,680,000, and then they're going to cancel out and going to remain with 0. That means this model is satisfied with this kind of measurements, and that one tells us that these calculations or these dimensions are optimal, and that's how the county government of Kisumu is going to trust you if you use this kind of a model to compute such problem and solve, so that they maximize the little that they have, so that they gain more and make more profit. Let's look at another example now for the case of a closed system. This one is also a growing company who wishes to invest its surplus. They have made some surplus, which is profit, and because they are still growing, they want to invest this surplus into constructing a hotel for rentals and other activities to raise more income. They purchased a piece of land and they decided that the building should be 8 meters high, covering a surface area of 592 meters squared of the land. So the land they purchased, they want to separate 592 meters squared for the building to build an hotel, so that they can raise more income from that hotel. And the estimated capacity of the building is 960 meters cube. Use Boas optimization model to Roman 1, estimate the possible values of the length and the width. Once you use Boas optimization model as a student, if you see such kind of a question, you just have to smile. You just have to smile because things are made easy with this model. Now then, Roman 2 say verify if the measurements are optimal. Of course, verification of something is very key and is very important, because it gives you an assurity, because before you invest your money into a business or into a certain project, as a company you have to consider so many things, because you don't want to lose your money. Your aim is to make more profit and make more income for the growth of the company and other activities that can be supported by the surplus. So let's go ahead and see how this company is going to apply Boas optimization model so that they can make more income. Into solution of the first question, which says we estimate the possible measurements of the length or the width of this kind of an hotel. So we have C as the height, which we are given. It's going to be constant as 8 meters high. The volume was provided as 960 and the surface area was given as 592. Because a building is a closed system, we have to note that a building is a closed system. So which means we are going to use the closed system model, which is 2a squared b squared minus aab plus 2av plus 2bv is equals to 0. Recall that from the expression of the surface area, we have the C as A is equals to 2ab over 2 into A plus B, then is equals to another expression of C, which is V over AB. We are given height C as 8, and the volume and the surface area, and we want to compute the dimensions, which are the length and the width. Now we are going to substitute what we are given into the expression of the C, of the height, and this is what we are going to have. We are going to have 8 is equal to 960 over AB. This implies that you are going to have, if you cross multiply, you're going to have 8AB is equal to 960. Dividing 960 by 8, you're going to have A times B is equal to 120. That becomes our first equation. Then secondly, we are going to have 596. That's now the first expression. 592 minus 2 into AB, and AB is 120 as we have gotten. So you are going to have 592 minus 2 into 120 over 2 into A plus B, which we still don't know, and we are yet to find out. We are yet to find out using Boas optimization model. As you can see, this model really simplifies things and break things down for easy optimization problems. Now, doing your simplification and calculations, this is what I got as equation 2. A plus B is equal to 22. Maybe just to tell you how that one came about, you cross multiply 8 times 2 into A plus B, and then this one is going to remain on the other side. Then you are going to divide. You are going to have something like 8B plus 8A is equal to 176. Then you are going to divide that. You are going to have A plus B is equal to 22, and that's equation 2. Then by factorization, as you can see, we have AB is equal to 22, and we also have A times B is equal to 120. Looking at a quadratic equation, of course, this one is going to lead us into a quadratic equation. But in this way, this is how we are ending up with our equation 1 and equation 2. But there's another way that if you use, you are going to end up having a quadratic equation, which you are also going to solve. So I assumed that this one is a quadratic equation, having A plus B is equal to 22 and A times B is equal to 120. By factorization, we are going to say that a number that can be two numbers that if you add, you are going to get 22, but if you multiply them, you are going to get 120. Obviously, these possible values of A and B can be 10 meters and 12 meters regardless. That means A can either be 10 or A can be 12, or B is 10 or B is 12. That means if A is going to be 10 meters, then B is going to be 12. C is going to be constant 8 as we were given by the management of the growing company. Or we can choose to take A is 12 meters, then B is going to be 10, and C is going to be constant, it's going to be maintained at 8, because the company management resolved that the height of this building must be 8 meters. So C, which is the height, is going to be maintained as constant. So those are the possible measurements of this kind of the building that the company wishes to build. Now let's go ahead and verify our results. It is good to verify if our results are optimal, so that we can be sure before we invest our surplus into a project. We have to be very sure that it's going to give us what we need. So to verify the results, we are going to substitute the values that we have computed into our model, which is Boas optimization model, and it's going to be confirmed. So we have there 2a squared b squared minus aab plus 2av plus 2bv is equals to 0. If that one is going to be satisfied with these values, then you are going to say that these results are optimal and they are very good, and they are going to give us higher returns, they are going to give us more incomes. So with my computation, I used the first possibility, which is A is 12, B is 10, C is 8. A I was given as 592, V I was also given as 960. Inserting that, I'm going to have negative 42,240 plus positive 42,240, which is going to cancel out, and then you're going to have 0. This means our results are optimal. Having verified that, we can happily say that our computations are optimal, and this kind of measurement is going to give us more income as required by the company. Now you can go ahead and use the other possibility when A is 10 and B is 12, C is maintained or constant as 8. You are still going to have the same result. You are still going to land at 0, which means whichever possibility you take, it is going to be optimal as long as you are after making more profit. So to the conclusion, Boas Cuboid models connect the geometry and the optimization. It connects the geometry. The geometry part is the length and the dimension part, and then optimization now deals with how you can apply this model to optimize your project for more income or for more profits. Then enhance design efficiency in engineering and commercial context. So that is the conclusion, and that's how this Boas model of a cuboid works. And that is that about the Boas cuboid models. We have done the derivation, we have seen the equations, which are the models, and we have seen the application. So this is the second model of which are recently derived, and as you can see, these models really works magic. They really work magic. Yeah, they are models that are recently derived. 2025 models, African models, and as I said, Africans, you must be very happy for this, and Kenyans, you must be very happy for this. I'm waiting for those people who are in charge of such things, of new innovations, to call me so that I may present this to the world for the benefit of our economy, for the benefit of Kenya, for the benefit of our continent Africa, and for the benefit of the entire world. These Boas optimization models will really do a lot if they are published. And to the engineers, this video is nice and these models works for you best. All you can do to this video is just subscribe, then you like this video and share, so that many students and engineers outside there can see how this new model is going to work for them. So share the video, and thank you for your cooperation, thank you for your time. Let me see the comment. What do you say about these new findings? What do you say about these new findings? What do you say? What do you have to say as the person who has watched this thing, as an engineer? What do you have to say regarding this model? Thank you for your time, and let's meet next time when I'm going to explain another model, of course the third model, which is the conical optimization model. Now we are going to deal with the cone in our next video. Thank you for watching. Have a nice time.